Welcome to Module 11. In today's module, we will be studying nuclear chemistry. Module 11 will be discussed in two videos. The first video will introduce the concept of radioactivity and the half-life of radioactive decay. After that, we will investigate the different types of particles that radioactive elements emit. In the second video, we will learn how to balance a nuclear equation. Finally, we will briefly mention some of the important applications of nuclear chemistry. The learning outcomes for Module 11 are: solve questions relating to the half-life of radioactive decay, and identify different particles that radioactive elements emit. Today's lecture is to introduce you to the main concepts of nuclear chemistry. Before we start, let's discuss some of the main differences between traditional chemistry and nuclear chemistry. In our previous modules, we studied principles related to traditional chemistry. For instance, we discussed that we don't create or destroy elements in chemical reactions. The reason is that traditional chemical reactions involve valence electrons only, and the nucleuses of these elements are not involved. Therefore, the number of neutrons and protons remains the same. However, in nuclear chemistry, we have different rules. For example, we create and destroy elements in the reactions because the reactions involve the nucleus of the atoms. Therefore, the number of neutrons and protons changes. In traditional chemistry, the sum of masses of elements and compounds in the reactant side before they go into the reaction is equal to the sum of the masses of the elements and compounds in the product side. On the other hand, in nuclear chemistry, the sum of masses of reactants is different than the products, and the missing mass is released as energy. Therefore, we will learn new rules to balance the nuclear equations, but don't worry, it will be easier than balancing traditional chemical reactions. The first concept we will discuss today is radioactivity. Radioactivity is the spontaneous emission of particles and/or rays from the nucleus of an atom. The symbolism and notation we describe for isotopes in Module 3 are very helpful in nuclear chemistry. You will recall that we have the symbol of the element, the mass number, which represents the total number of protons and neutrons, and the atomic number, which indicates the number of protons. The principal emissions from the nuclei of radionuclides are known as alpha particles, beta particles, and gamma rays. Upon losing an alpha or beta particle, the radioactive element changes into a different element. There are a few particles that you will need to learn. A neutron has the symbol 1/0n. The atomic number is 0 and the mass is 1. A proton is 1/1h. The atomic number is 1 and the mass is 1. A beta particle is an electron and has an atomic number of -1 and has the symbol 0/-1 E. An alpha particle is a helium nucleus with the symbol 4/2 He. This has an atomic number of 2 and a mass number of 4. Radioactive elements decay by themselves over time. Some decay very slowly, while others decay quickly. To account for this property, we use the concept of half-life. We define the half-life of radioactive elements as the time it takes to disintegrate 1/2 of the element's mass. The half-lives of elements range from a fraction of a second to billions of years. The table below shows some examples of different elements with different half-lives. For instance, radium has many different isotopes, some of which drop in mass very quickly. For example, the radium-223 isotope has a half-life of 11.7 days. The radium-226 isotope, on the other hand, has a half-life of thousands of years. Let's practice some examples related to the half-life concept. Suppose we start with 1 gram of the radium-226 isotope, which has a half-life of 1,620 years. So, after 1,620 years, the element decays and the mass drops to 0.5 grams. After another 1,620 years, the mass will drop to 0.25 grams, and so on. Please note that in the exam you will get a similar question with simple numbers, so you can count to solve the question. Let's see another example. The half-life of this iodine isotope is 8 days. How much of the isotope from a 32 gram sample remains after 5 half-lives? The starting point is 32 grams. After the first half-life, the mass drops to 16. After another half-life, the mass drops to 8. After the third half-life, the mass is 4 grams. The fourth half-life will make the mass 2 grams. And finally, after the fifth half-life, the remaining mass is only 1 gram. Therefore, starting with 32 grams, only 1 gram of the isotope remains after 5 half-lives. As we mentioned earlier, radioactive elements emit different types of particles or rays. The first type we will cover are alpha particles. An alpha particle consists of 2 protons and 2 neutrons and has a mass of about 4 AMU and a charge of +2. An alpha particle has a structure similar to a helium nucleus and is usually given one of the following symbols: the Greek sign alpha, or 4/2 He. When an alpha particle is emitted from the nucleus, a different element is formed. The atomic number of the new element is 2 less, and the mass is 4 AMU less than that of the starting element. To balance the nuclear equation, we need to balance the atomic and mass numbers between reactants and products. In this example, uranium emitted a particle and changed into thorium. This particle is an alpha particle. We can also write the chemical equation using the helium symbol. Let's check if the nuclear equation is balanced. The mass number for uranium is 238. The mass number for thorium is 234, so there is a difference of 4 AMU. This mass is balanced by the helium nucleus. The atomic number of the uranium is 92, and for the thorium it's 90, so that's a difference of 2, which is also balanced by the helium nucleus. Let's see another example. Radium emitted an alpha particle and produced radon. The nuclear equation can be written as such. Some elements emit beta particles or go into beta decay. So what is a beta particle? A beta particle is identical in mass and charge to an electron. Therefore, it has a charge of -1. Both a beta particle and a proton are produced by the decomposition of a neutron, according to the following chemical reaction. The beta particle leaves and the proton remains in the nucleus. The beta particle is written as the Greek sign beta, or 0/-1 E. When an atom loses a beta particle from its nucleus, a different element is formed that has the same mass, but an atomic number that is 1 greater than that of the starting element. For example, the thorium-234 isotope goes into beta decay and produces protactinium-234. The equation can be also written as such. The mass number for thorium and protactinium is equal. However, the protactinium has an atomic number of 91 compared to 90 for the thorium. Thus, we need a beta particle to balance the equation. Let's look at another example. Lead emits a beta particle and changes into bismuth, as per the following equation. Remember from Module 3, Part 2, we discussed wavelength and mentioned that gamma rays have high energy and a short wavelength. Gamma rays are photons of energy. A gamma ray is similar to an X-ray, but is more energetic. It has no electrical charge and no measurable mass. Gamma rays are released from the nucleus in many radioactive changes, along with either alpha or beta particles. Gamma radiation does not result in a change of atomic number or the mass of an element. This is the end of part 1 of module 11. Please proceed to the second part to learn how to balance nuclear equations and learn some of the applications of nuclear chemistry.